right, welcome back, my beautiful calc students. Let's move on to example 5, using the natural log function with integration. I have sine x over cosine x I'm trying to integrate. The first thing I recognize is that sine x divided by cosine x is tangent x. And I know that the derivative of the tangent of x would be secant squared x, but I don't know the integral of tangent x. And we've never talked about the integral of tangent x because we didn't have our natural log before now. But I am looking at the function. I do see a fraction. I do notice that with this fraction, if I took the derivative of sine, it would be cosine. But you never, ever, ever want your du on the denominator of your function, ever. So don't ever go that route. Take the derivative of cosine. The derivative of cosine x is sine x. Is that true? Negative sine x. Okay, so I'm off by a constant multiple. But that's okay. I can multiply through by a negative and change that up a little bit. Okay, so we're going to go to the side, and we're going to say let u equal cosine x. Du, therefore, is negative sine x dx. And I don't want a negative sign. There's no negative sign here, so I want to get rid of that negative sign. I'll divide both sides by negative 1, and I'll have negative du is equal to the sine of x with respect to x. Okay, so up here, I have my sine of x dx becomes a negative du, and I have my cosine x is my u. I can rewrite this as 1 over u times negative du. Now instead of negative du written here, I'm going to put my negative out there and my du right there. I still have negative du. I'm just choosing to put my constant to the outside and save a step. Alright, this is negative natural log of the absolute value of u plus c. I do a plus c because I don't have a definite integral. This is an indefinite integral because I don't know what it is. So I'm going to bring my u back into play as an x. This is the negative natural log of the absolute value of cosine of x plus c. And that looks like a handful, sounds like a mouthful. It is a lot. We will be having natural log with trig functions inside, and sometimes you actually have natural log of another natural log inside your absolute values. But this is our answer. We can just check this quick, like with our head a little bit here. The derivative of cosine would be negative sine, but this negative will counteract the derivative's negative. Give me a positive sign on the numerator, cosine x on the denominator. I'm good to go. I'm just doing that mental check for that derivative. It will check. All right? So much for example 5. This is a pretty easy trig function to know. And by the way, you can actually memorize this now. This is now the integral of tangent x with respect to x, because sine x over cosine x is tangent x, is now the negative natural log of the absolute value of cosine of x plus c. So this is one of those formulas or rules that they print on the inside cover of your calculus book. That's how important it is. You either memorize it or be able to derive it if you need to. Okay? All right. Okay. So much for that. Let's do another trig function. We'll do something else instead of just sine over cosine. How would it work if I went the other way around? Cosine over sine. Let's give that a try. Except maybe not even asking you it that way. This is example 6 now. Let's say I give you the integral, and instead of asking you cosine x over sine x, I ask you instead about cotangent x. I know the derivative of cotangent x, and the only reason I know that is because I know the derivative of tangent x. The derivative of tangent x is secant squared x, and therefore the derivative of cotangent x would be negative cosecant squared x. But I don't know its integral. I don't know how to work backwards from the cotangent x answer to get my original function. So I'm going to have to do something. I'm going to have to rewrite it and look at this thing in some other format that maybe I can find some applicable situation. So cotangent, we know, is cosine x over sine x. And now we look at this, and we could go either way. We could take u as my cosine, and the derivative of cosine x is negative sine x. We're off by a constant multiple. But remember, I never, ever, ever want my du to be down in the denominator. The du always has to be in the numerator. This du right now this is a dx, but this dx right now is in the numerator because it's dx over 1. So it's definitely a numerator factor, never ever in the denominator. So therefore, if I let my u equal sine x, the derivative of sine x is cosine x, my du would be up here. And that's going to work perfectly. I'm not even off by a constant multiple. I have it exactly the way I want it. So we're going to let u equal sine x. Du therefore equals cosine of x with respect to x. And I can come over here, and this is my du, this is my u. This now gets rewritten as 1 over u du. Back to theorem 5.5, and our answer is natural log of the absolute value of u plus c. However, we need our x's back in here. So this becomes a natural log of the absolute value of the sine of x plus c. I definitely need the absolute values because sine x I know alternates between a positive 1 and a negative 1 and a positive 1 and a negative 1. And I have to make sure that that power is always positive. And this is good. So we can write another rule like we did last time, and we can say that the integral now of cotangent of x with respect to x is equal to the natural log of the absolute value of sine of x plus c. And again, this is going to be one of those formulas that's written in the cover of your book. All right? So you either memorize it or you know how to derive it. Okay. Let's do another trig function. Let's get a little tougher with our trig functions. Let's go for example 7 here. All right. Example 7 is asking for, and this is a really tricky question here, if you ask me, the integral of secant of x with respect to x. I know the derivative of secant x is secant x times tangent x, but I don't know the integral of secant x. And if I change secant x in terms of sine and cosine like I have the rest of the work we've been doing so far, secant x is just 1 over cosine x. I wouldn't have my sine function involved for me to do my u substitution the way I want. So this is an extremely tricky problem, and it kind of brings me back to when we did limits. And if you had square roots involved in your functions, you kind of multiplied by the top and bottom of your conjugate and eliminated your square root with the difference of squares. This kind of reminds me of that because I have to introduce something to this problem that's not already sitting there. And if I didn't already know how to do it, I don't know as if I would ever create this next piece. So don't ask yourself, how would I ever do that? And now that you've seen it, you're going to be expected to do it. However, I wouldn't have expected anybody to come up with it on their own without any prior knowledge of watching this video or reading your book. Okay, so this is what we're going to do. We're going to take the secant of x and we're going to multiply it by some fraction with the same thing on the numerator as what's on the denominator. And that thing that I wouldn't expect anybody to come up with until now, you're going to have to after now, is secant of x plus the tangent of x over itself. Secant x plus the tangent of x. And then your dx is to the outside. Now secant x plus tangent x divided by secant x plus tangent x is really the number 1. So I am not changing the value of my problem, I am just changing its appearance. I'm rewriting it so that maybe I can get somewhere with this. Now I'm going to take this secant x, which is really over 1, and I'm going to distribute it over the two terms on that fraction. So I end up with secant x plus secant squared x, because I have secant x times secant x is secant squared x, plus secant x times tangent of x, all over 1 times anything is anything, so just copy secant of x plus tangent of x with respect to x. Now you take a peek at this again, and it's the same equivalent as what we started with, but it looks a lot different. And hopefully now, what you see on your denominator, if you're thinking of taking the derivative of secant x plus tangent x, and I'm hoping you are, to see if that happens to be your numerator, you get the numerator. It's just that the numerator is reversed. The derivative of secant x is this secant x tan x, and the derivative of tangent x is this secant squared x. So if my u where the denominator, secant of x, I do that all the time, plus the tangent of x, I'd like a u in there, thank you. Then my du would be, the derivative of secant x is secant x tan x plus sine, what's the derivative of tangent x? That would be secant squared x. And all of this gets a dx. And if you look, that is my numerator. It's just turned around. I'll turn it around right here for you if it helps. I will go ahead and write the secant squared part first. I'm allowed to turn anything with addition around because addition is commutative. So secant squared x plus the secant of x times the tangent of x. Wrap that in brackets and multiply it by dx. And I definitely have all of this stuff here is now du, and everything on my denominator is now my u. So this is pretty sweet. We get 1 over u du. And we get that by introducing this binomial over the binomial. Again, I would never have thought that off the top of my head. I wouldn't expect you to have thought of it off the top of your head. However, now that you've seen it, I definitely expect you to utilize it. Okay? Be able to recreate it if I ask you to. This is now, I can integrate, this is the natural log of the absolute value of u plus c. Bring my x's back into play. U is equal to secant x plus tangent of x. And my absolute values, add my plus c on the end. And I am finished. Okay? And this check is a little more complicated, but I think I'll do it with you. All right? Let's see if I have enough room over here. I think I'll erase my u substitution and I'll do my check right in the middle of where this was. So here's my check. Always tell me where your check is on your page too. Don't just start doing something else because then I think you think it's part of the problem. So communicate effectively with me. I want the derivative now with respect to x of this whole entire thing I just boxed. The natural log of the absolute value of the secant of x plus the tangent of x, close my absolute values, and plus c. So when I take the derivative of my natural log, the power, or the thing the natural log is being applied to, goes on my denominator. So I have secant x plus tangent of x. And the derivative of this u, or of this power, goes on the numerator. The derivative of secant x is secant x tan x. Plus sign is copied, and the derivative of tangent x is secant squared x. And then plus 0, because the derivative of any constant is 0. So this is all I have here. It doesn't look like secant yet, does it? But do you notice on the numerator you have a common secant? So you factor that common secant x out, and you'll be left with, I'll have a tangent of x right here, plus, and if I factor out one of my secant x's, I'll still have one more, so secant x again, all divided by this denominator, which is secant of x plus the tangent of x. And I'm hoping that you can see this denominator is the same thing that's in this set of parentheses, except it's turned around. Okay, this can divide off, this can divide off, and all I have left is secant x, which is exactly what I was asked to integrate up here in my anagram. So I'm checked. Okay? Alright, I think I am going to stop right there. I'm going to come back and give it a try. Let me just check my time. Yep, I think 14 minutes is a long enough video, so I'm going to say talent out and we'll be right back. Thanks.